Take it off. Take it off.
Okay. So I'm hoping everyone has seen Interstellar.
Woo!
Okay. So you must have seen the black hole Gargantua in it. If you have not, it's fine. I'm just going to go through the comparison between the actual black hole that we have pictured and the Gargantua. So yeah, this is the movie Gargantua. Do not be alarmed by the warning, please. I'm hoping you're not confused by the end of this. Yeah, so we'll just move on to the basics of black hole for now. So black holes are high concentration of mass, which is fit into a small compact body. So when a star explodes, it usually, if the mass is high enough, it goes down into a black hole or a neutron star, depending upon how high the mass is. And the black hole is segregated into 3 different types of mass categories. So we have the stellar mass, which is 5 to 10 times the mass of the sun, and it can be seen throughout the galaxies because they are like too small. Then we have the intermediate mass black holes, which are from 10 solar masses to 100,000 solar masses, which are also throughout the galaxy. But the supermassive black holes are from 100,000 to 1 billion times the mass of the sun, which are usually found in the center of big galaxies. In our galaxy, the Milky Way, we have the black hole named Sagittarius A star. The name for the Sagittarius A star is because it can be seen in the constellation of Sagittarius in the night sky. So we have, that it's easier to understand where stars are located in the sky. So it is estimated to have a mass of 4 million times the solar masses. So basically it comes under supermassive black holes. Moving on. So this is a basic animation of Gargantua. We'll talk about the properties of Gargantua and then we'll start comparing it. So Gargantua is a massive spinning black hole. It has the planets Miller and Mann surrounding it, as well as a neutron star, which is very close to it. It is 100 million times the mass of the sun, which is around 25 times the mass of our Milky Way black hole, that's a Sagittarius. The spin is close to maximum. It's close to maximum because there is a limit to how fast any planet or any object in the universe can rotate. After that, it disintegrates, it can't hold up its mass. So the Gargantua was actually constructed or simulated with the help of a scientist, Kip Thorne. So it's made based on actual real values of how black holes are in the universe. So Gargantua was basically quite accurate when it came to simulating a real life black hole, except one key detail, that's Doppler effect. So a Doppler effect, basically, the accretion disk that you can see that's near to us, the mass or matter that's surrounding the black hole is nearer to us, is usually bluish in color, and the mass that's far away from us is usually dimmer or hotter. So it's reddish in color. So that key detail was removed from the movie itself because the astronauts that were actually rotating the black hole were way too close to it, so the black hole is way too bright for them to understand the difference in Doppler effect. Fun fact, every second of Gargantua that they simulated took them 100 hours of work. So every person who made a second of a frame took 100 hours of just 1 second. I mean, we see like around 10 minutes of it, so that's a lot of work. Moving on. So this is the actual real image that we saw in 2019. So this is the first image of a black hole that's in the galaxy M87. It is 6.5 billion times the mass of the sun. So it's 600,000 times the mass of Gargantua. So you can understand how big this is. So you can see the event horizon. So the event horizon is usually at the corner of the black hole, so that's the area from where not even light can escape. We have the singularity, that is the center of the black hole where all the mass is concentrated. We have the accretion disk, which is all the debris that's surrounding the black hole. And then we have the photon sphere, which is basically photons emitted from a plasma. So you can see that there's a little difference from the gargantua that you saw and this image that we have photographed, but that's just because of the inclination angle. So to see the inclination angle, you can see the first and the last row is how gargantua is viewed. So that's from the 0 degree, and the middle two lines is how we have pictured the black hole. So that's from top down. So that is why you cannot see the rings similar to how gargantua is seen. Yeah, and even in gargantua, you can see that there's rings on top of the black hole and at the bottom, but that is because of the gravity that affects the, like you can see the accretion disk that's behind the black hole and is projected on top and the bottom of the black hole. It's just the lensing effect. This is the black hole in the center of our universe, center of our galaxy. That's Sagittarius A. It's a little blurrier compared to the M87 one. That is because our black hole is way too small. So the matter is moving way too fast for them to piece together all the images. Moving on to the detection. So black holes are generally detected using these 4 categories. So first is the gravitational lensing. That can be seen in the black hole itself. This is an Einstein ring that shows 2 different galaxies. So one of the galaxy is actually magnified because of the middle galaxy. Second is the colliding black hole. So we had our first detection of 2 colliding black holes back in 2015, and the movie was made in 2014. So we were not even sure if black holes actually existed in the universe, but we already had a simulation of it, which was almost accurate. So, then we have the X-ray detection. That's usually from the accretion disk. So the accretion disk is so hot that it usually emits EM radiation. And last we have the gravitational pull on the object. So this is the actual Sagittarius A star in the center of our galaxy, and this is the gravitational effect that it has on stars that's surrounding them. So these are actual neutron stars or huge mass of stars that are actually surrounding it. And thank you. I hope it was not too complicated.